Good morning, everyone. I'm Pratik. I'm a software engineer at Figma. I work for the infrastructure team, mostly on their caching and database infrastructure. This talk is about my time at Momento, which was last year. I moved to Figma last year from Momento. And I'm going to talk about how we built Protosockets to go beyond HTTP and gRPC. Previous to Momento, I also worked at AWS on their marketplace data platform team and the DynamoDB control plane team. In the spirit of SREcon, I would like to say I'm a firm believer in reliability is like oxygen. You only realize once it's absent. So having said that, I'll just kick off. So if you all don't know about Momento much, Momento is a Series A smallish startup. They are a caching and a PubSub platform. So if you want to use a cache from your mobile device, from your web device, or from within your servers, it provides you with KV store to do that. This is a very high-level initial architecture, circa 2023, 2024, that I have here, where as a client, you use Momento's SDK. You make a request that goes over the NLB. It hits one of the internal routers. Let's say it's a GET request or a SET request, two very simple KV APIs. The router would do some parsing of that request and send it to the storage servers. The storage servers either store the request or send you back the response based on that particular command that you send. There's a control plane. The control plane is what we like to call as the brain of the system. It is responsible for sending metadata to routers. So for example, when you create a resource, the control plane is the one that has all the state. It knows which partitions, your resource or cache has how many partitions, which storage servers it belongs to. So it sends all of that metadata information down to the routers. It also does the health check and provisioning of the storage servers. So if you have read the GFS paper from 2000, this seems very familiar. In my experience over the last, not a lot, 10-ish years, I've seen most distributed systems start falling into this particular pattern of a stateful control plane, a stateless router layer, and then your actual storage layer or sandbox layer for compute, like that. So yeah, this was the initial high-level architecture. Before I talk about any of the performance stuff, I would like to call out what we used as our benchmark setup. For the actual benchmark itself, we use RPC perf from Twitter. It was written back in Twitter. Twitter had a huge caching infrastructure back in the days when it was called Twitter. We use this library. It's currently owned by IOP Systems. It's another startup that operates this library now. So our client was a 4XL, which is 16 cores. We want a fat client so that it's not the bottleneck when you're doing benchmarks. The router was a 2XL, which is around 8 cores. Your storage servers with 2 cores. Our workloads were with an item size of a kilobyte with a read-write ratio of 1:1. So you have 50 gets and 50 sets, for example. OK, so going back to the initial architecture, we were historically a gRPC shop. So every request from the SDK to the router, all the way to the storage, the control plane talking to these components, all happened over gRPC. When we ran our benchmarks on this particular architecture, we saw around 20,000 operations per second with P39s less than 5 milliseconds. So this is the way we usually benchmark caching workloads. At my time at Figma, currently too, previously at Momento, previous to that, we always kept a ceiling for what the latencies our clients or customers desire, and we see how much throughput we can extract out of our servers as that baseline latency. So 20,000 operations per second, is that good? Is that bad? How many of you think it's bad? Well, it's kind of underwhelming, right? And how do you know it's bad? So what we did, we stripped out the routers. We saw, OK, let's try to hit the storage servers directly. Sure, you have a router, you have a connection pooling layer. It's going to add some overhead, but what exactly is that overhead? So we stripped off the routers. We directly pointed our RPC perf client to the storage servers to see what they can do. And that came out to 200,000 operations per second. So it's an order of magnitude less when you add a new component, which is kind of underwhelming. It's sure, you have overhead, but not an order of magnitude. So where does this overhead come from? Before you optimize anything, you got to see, you got to measure and see where your system kind of breaks. So gRPC itself, it has a network overhead over the wire. So there's a byte on the wire tags with your HTTP2 frames, the gRPC headers, the actual protobuf envelope that you're sending as a part of the request. Apart from this overhead, or more importantly, you pay a CPU tax. You have these gRPC state machines, interceptors, error handling, all of those things that makes the framework beautiful, that makes the framework as stable and good as it is, but at the same time, you're also paying an additional cost for it. That cost results in added latency for your clients or for your customers, less throughput for your internal servers, which directly impacts your bottom line. So now, let's say you have a big customer and you have to support 1 million operations per second. Based on the numbers I told you before, you need like 50 routing servers itself, which, it might cost around hundreds of thousands, somewhere around $100,000 in the AWS world. It's like a ballpark number that I'm just throwing out here. So if you're building SaaS, if you're building infrastructure as a service, your bottom line matters a lot. You have to reduce the cost or reduce the server so that you get more margins for your business, so that your business is actually profitable and you're not spending like a shit ton of money. Sorry about that language. Okay, so before any particular manual or before reinventing any kind of wheel to get more performance from your servers, gRPC has its own streaming library. So for example, in the previous slides that I showed, every request you send as a client translates to one HTTP2 or gRPC request for the router, one HTTP2 or gRPC request for your storage servers. So why not let's open one long-lived stream and send those requests over that. What you do with that is you reduce your per request overhead. You're still paying your per stream overhead, but on one HTTP2 stream, you're sending all your requests. So that did result in lower network overhead. It did result in lower CPU overhead. And we did see a 20 to 30% throughput boost by just switching from gRPC unary to gRPC streaming. So that amounted to around 25,000 operations per second from 20,000 operations per second. So around a 20% throughput boost. There is a downside when it comes to some of these streaming libraries. Your implementation becomes a bit more complex. I don't know if I can say that with Cloud Code anymore, but who knows? Like it's still a little more complex compared to when you're dealing with unary libraries. Okay, before I show this slide, actually, yeah, okay. So this is, before I dive into this, Momento is primarily on Rust. Rust is one of the high-performance languages that's used by a lot of new database and performance companies these days over traditional languages like C++. Well, I shouldn't say traditional, but yeah, over languages like C++ or C. So this is how the Rust gRPC stack looks like. The asynchronous Rust gRPC stack looks like. You have gRPC at the top. You have H2. H2 is async Rust's HTTP2 library that's built on top of TCP. It uses MIO as a library over UNIX. So if you're familiar with system calls like read, write, open, MIO gives you a friendly abstraction over those system calls so that you don't have to deal with them yourselves. MIO internally uses glibc, which is the UNIX library. And then finally, you have the hardware abstraction layer at the bottom, where you're using assembly to talk to your hardware components. Now you can see the heading of this particular GitHub issue that says library does not scale with multiple cores. So once we started, and this is still open, once we started digging into why we're seeing like such less performance even with the streaming ecosystem, we ran into this issue, and we saw that we started doing experiments or measuring different things, and the one thing that helped us the most were flame graphs. So flame graphs are basically the width that you see here that indicates how much time every function consumes, and the height that you're seeing here is basically the depth of your call stack. So it just basically lets you visualize how much time your system is actually spending on different parts or different components. So going back to this particular slide, we were seeing a lot of task starvation. Now, what does that mean? By task starvation, I mean that every request that the client sends that reaches the routers, they were all blocking on shared state. Whenever you have shared state, you need to synchronize the shared state to avoid corruption. And each of these requests were going and blocking on a particular lock or mutex behind that shared state. When requests block, they park themselves on the kernel for almost hundreds of microseconds. And they can only make progress once the kernel actually wakes them up. So that directly impacts your throughput and latencies for the client side, which is what we saw in this flame graphs. But this is not the direct flame graph. We unfortunately did not have that from what we tested, but we did not see like a giant width saying lock contended on a particular request. It was not very easy to spot it directly. We had to literally, using buttons and eyes, click through every individual frame. So if you click on an individual frame, it will expand out. And within them, we saw these lock contended or mutex parts sprinkled all over the flame graph. So even in the streaming world, when you're using gRPC streaming, the shared buffer is across streams. So it's possible that your runtime threads are actually blocking for every request that is coming in the router. So you have 6 OS runtime threads, every request comes in. It's possible one is working on it and 5 threads are blocked on that shared buffer. And that was our hypothesis. Like, that was the only thing that was making sense, especially with that open GitHub issue that also we had, that this particular shared state or this particular mutex on this shared state in the H2 library was causing this throughput drag or the latency drag for our clients and for our servers. So this was one of the libraries that my mentor at that time and we were working on. There's a GitHub link, kvc/Protosocket. So we pulled it out from like a pet project, and we were like, okay, let's try this in our systems and let's see what it does. So Protosocket is a non-blocking bidirectional message streaming connection. You just need to provide your serializer and deserializer for your messages, and you can stream to and from TCP servers. There is no wrapper, like there is no HTTP2 or gRPC, no WebSockets. You just depend on TCP and your serialization strategy. The dependencies are very trim. It just uses Tokyo, which is, again, asynchronous Rust's runtime. And there is minimal synchronization points. There is no shared state connection between different streams or connections. Every connection has its own individual buffer and isolated state. You can use multiple encoding formats. You can use JSON. You can use protobuf as you like. It doesn't have too much opinions. If you want to create an ordered stream over TCP, reinvent HTTP, you're free to do that. If you want unordered, non-blocking streams, reinvent UDP, you're free to do that. So we just pulled out this library and started experimenting it with on our servers. Again, like just some more information about Protosockets. So what it does is now we get rid of those 2 additional layers that I was speaking about previously. Now you're directly on the TCP land. You don't have the overhead that's associated with gRPC. You don't have the overhead that's associated with H2, that is the HTTP2 library that we were dealing with. So after this, we started seeing, I'll come to the numbers, but we started seeing almost 60 to 70,000 requests per second or operations per second on our routers, which is almost a 3x boost that we were getting before with gRPC streaming or gRPC Unary, which is what I've written here. This is the final architecture. Now, initially we only had Protosocket between our internal router and storage servers. We did not expose it to the outside clients because that's just easier. You're within an AWS VPC, you're in control of your own servers, you can change the protocol however you like. But before you open it to the world, there are much more considerations that we need to think about. So this gave us 70,000 operations per second with our 5 milliseconds baseline. Now, this is after I sort of left the company, but in the last few months, they have been experimenting with opening Protosocket to the client SDK as well. Right now, it's only available on the Rust SDK. So if you go to like Momento, Rust SDK, you can actually see Protosocket being used to talk to the routers directly. So how does this work? I'm just going to drink a little water. So when you open it to the client, now your client SDK, the first thing it does is it talks to your control plane to discover all the routers. This is over plain HTTP. It refreshes every 30 seconds to make sure it has the latest state of the world. Once it has discovered all the routers, it bypasses the NLB and starts talking to the routers directly. How do you authenticate? How do you authorize, right? Like that's probably the first question that might be coming to your mind. Talking to the control plane itself is over auth0, auth0, so you have like, it's over HTTP, so you have like just the basic authentication that's happening over there. When you're talking to the routers from your client over the public internet, the first message that you send over Protosocket contains your JOT token. So the way you authenticate in Momento, you have a self-contained JOT token that controls both auth0 and auth0. So the first message or the first frame that you're sending over Protosocket will contain that authorization token, and the routers will use that to authorize. Then over the same connection, your messages start flowing, and the router interacts with the storage servers, again over Protosocket, and sends back the response. These arrows should be bidirectional here, kind of, it shouldn't be single direction. While I'm talking now, I realize that. After opening to the client, we are still seeing 70,000 operations per second, but now our PH39s dropped from 5 milliseconds to less than 3 milliseconds. We probably could have like gotten a more throughput boost, but we wanted like that additional latency benefits that we're seeing by opening it to the client. So this is the architecture, how it looks like today. There are 20 different client SDKs that Momento has. This is only baked into Rust and I think Golang right now. But in the future, we're planning to use foreign function interfaces so that all of these different languages can directly talk to the Rust client, and we don't have to reinvent the wheel in every different client. Again, as I said, implementation for the team itself becomes a little more complex when you're dealing with these custom protocols. Not for you as a customer, but for the internal team who's actually managing these services. Okay, so the numbers recap. We started with gRPC Unary, 20,000 requests per second. Then we went to streaming, 25,000 requests per second. We went to Protosocket only between the internal systems, between the router and the storage servers, at 70,000 operations per second. And then we opened it to the client. We still got more than 70,000 operations per second, but more importantly, we saw a huge latency win in that, almost 60% at P39s. Okay, so coming to trade-offs, I think I've mentioned more complex implementation a couple of times. As a systems team, if you're trying to build this on your own, if you're trying to build these protocols, if you're letting go of HTTP or all the nice things that gRPC and HTTP have, you'll have to deal with like more complex implementations and possibly reinvent some of the things that they already provide. But also let go of the things that you feel is redundant and not required for your particular system or your particular workloads that you're running. HTTP has better interoperability. Load balancers, proxies, firewalls, they're all aware of HTTP, so this won't be trivial to open it to customers behind corporate proxies. You can still use it within your internal servers, but once you go outside to the public internet, it becomes a little tricky. The tools are all HTTP aware, so logs, metrics, on-by dashboards. You again have to do much more work to get all those things back that you were previously sort of getting for free when you were over HTTP. So some of the key takeaways, measure, then optimize. A lot of times we fall into the trap of let's start optimizing without like just seeing what the problem is. Measuring can take different forms. We should be looking beyond traditional logs and metrics, using tools like flame graphs. There are a lot more. Brendan Gregg is one of my favorite people in this world of performance tools. So you can refer a lot of his books and blogs and articles to see which is the right tool for the right thing that you're trying to optimize. Community-maintained ecosystem needs more love. Like one of the things when you're using languages like Rust is most of the things are community-maintained. So you can't like just trust them blindly. You have to see what pitfalls they have, like we figured out with that particular shared state contention that we were running into in their HTTP2 library. But standard library is also not always the best either. I didn't have too much time. I could have, because that would have taken a talk in itself, but we actually also initially rewrote the standard library mutex or the lock with our own mutex, which just used to spin faster. It was a spin lock. It used to spin faster. And we got a 10 to 15% boost with that too. But not so much after we moved to gRPC streaming. So we just got rid of that entirely and started playing around with Protosockets. Finally, when do you use this? I think these undertakings are only worth it if it impacts your bottom line. As I mentioned initially, now with 20,000 to 70,000, that million operations per second workload, we can do with 20 servers instead of 50 servers. So that's 60% savings directly for your company's revenue, which directly impacts your company's profits. If you don't care about every single milliseconds, if you're on the application layer, probably not worth it, right? But if you're building a SaaS service, if you're building a performance-sensitive service, it might turn out to be worth it, depending on what your customers' workloads are and what your current revenue numbers look like. This is my personal experience when even though I was, before Momento, I did work on database teams, but I was mostly on the control plane layer. After that, on the data platform team, I was closer to applications, product teams between the infrastructure, but I was not necessarily closer to the metal, and I was craving that. So I moved to Momento to go closer to the metal and see how it actually works. And I went into this huge rabbit hole of where do I start? Like, this stuff is so hard. Like, where do I start? And I kept moving between like abstraction. So this is like the Rust programming language. Then you have async await, or the asynchronous I/O within Rust. Then you have your Linux, which gives you the system calls that this asynchronous frameworks are built upon. Then you have the hardware, and you probably might just open your computer and see what's going on inside. But I did not go that far. I wish when I started 10 years back in distributed systems, I first opened an operating system book to figure out, or to just recap how an operating system actually works, because a lot of the challenges that you will solve with one single Linux server or single OS sort of translates to when you're dealing with multiple machines. So some of the resources that help me, these are all free. They're all open source. You don't have to pay for any of them. OSTEP book, it helped me a lot. It's operating system in 3 easy pieces. It was 15 years I went to school, so this book helped me a lot. The second is Atomics by Mara Bose. It's, again, a free book by Mara Bose. She's exceptionally well written. Even if you're not from Rust background, I would say 60% of the book would still help you understand how locks and things work, because she makes you implement them from scratch and by giving you very granular detail and very beginner friendly too. Brendan Gregg is one of the sort of gurus in performance. His blogs and books are always very valuable. And the last one, this is the MIT 6.824 distributed systems course. After you go through the OS stuff, you can start looking into this one. I really like this course because it gives you 15 foundational papers. And I feel like most of the things that we work in the system space in day-to-day land sort of fall in those 15 papers somewhere or the other. You can easily create a mental model of how these systems work just by having some traditional or conventional knowledge about how previous systems were built. Just as an acknowledgement, this is my mentor, and that's the founder of Momento. Just thanking them for the opportunity that they gave for me to come here and talk about Protosockets. Yeah, that's it from me. I know I'm a little early, but yeah.